Okay, now that we have established that these are the only two costs that we have to account for, ordering cost and holding cost. So let's look at how to develop expressions for those two costs. And for that, we need to look at what actually happens to inventory over time. So here is a graph that represents how much inventory we will have in stock given the assumptions. So given these assumptions, demand is constant, lead time is constant. So then demand is constant, meaning the inventory level, if we start at this point, then it's going to go down at a constant rate because the demand is constant. Okay. Now, since we know what exactly is the lead time, we can calculate how much the demand will be during lead time, and when our stock reaches that point, then we can place an order so that right at the moment that we run out of stock, the order that we placed will come in, and the order, let us assume that the order quantity is Q. So the inventory reaches 0 and we receive a shipment of Q units. So the inventory jumps up to Q and the process repeats. Then again, demand being constant, it just goes down at a constant rate, and order having been placed at the precise moment needed, when the next cycle inventory reaches 0, the new shipment will reach and the quantity will shoot back up to Q. So this process will repeat over and over again. So this is the pattern of usage over time for our inventory. Okay. So given that, let's look at how to compute the cost. Here, ordering cost is how many times we place the order. We place an order, how many times we have to order, times cost of placing one order. Okay, so that's ordering cost. Okay. Annual carrying cost is the average inventory multiplied by the cost of carrying one unit per year. So, which means that we have to come up with an expression for average inventory. The average inventory turns out to be our order quantity divided by 2. Why is that? Well, in one given cycle, we start with Q and we end the cycle with 0. So the average is Q plus 0 divided by 2, Q over 2 for this cycle. The same thing happens in the next cycle. We start the cycle with Q and end the cycle with 0. So Q plus 0 over 2, Q over 2. So every cycle the inventory is Q over 2 all through the year, and therefore the annual average inventory, okay, the inventory level on the average will be Q over 2. So now let's introduce some notations. So Q being the number of units that we order, quantity, order quantity. Okay. EOQ is the optimum order quantity or economic order quantity. Okay. So, and here these three things must be known to us for us to be able to compute EOQ. So the uppercase D being the annual demand of units, okay, in units for the inventory item. Okay, what is the annual demand? Then C sub O is cost of placing one order, and C sub H is the holding cost or carrying cost per unit per year. Okay, so given that, now let's look at annual ordering cost. Annual ordering cost, remember, is how many times we order times the cost of placing one order. So if we have D as the annual demand, and if we order at the rate of Q per order, then D over Q will give us the annual demand divided by the number of units of each order. D over Q will give us the number of orders placed. And then you have to multiply that with cost of placing one order. So D over Q times C sub 0, that will be your ordering cost for 1 year. So this is how many orders we place in 1 year. Okay, that one. And then this is cost for one order. So this will be ordering cost for 1 year. Now, inventory cost, okay, as I said earlier, It's the average inventory times carrying cost per unit per year. So that will be Q over 2 is your average inventory. We discussed that just a few minutes ago, times C sub H. So that will be our annual inventory carrying cost or inventory holding cost. So the sum of these two is the sum of this plus that. That's our total cost. Okay. So now let's plot these two costs over Q. So the x-axis is Q. So if you look at carrying cost is Q over 2 times C sub H, or in other words, it's C sub H over 2 times Q. So which is a straight line, which is what this is. Okay, when Q is 0, it will be 0 times C sub H, it will be 0, and then it will increase with the slope of CH over 2 as Q increases. So order quantity goes up, it keeps increasing. All right. Now the ordering cost is D over Q times C sub 0. So Q is in the denominator. So this is not a linear cost like the holding cost. So you're going to, if you plot that, you're going to see a nonlinear curve. And you see that it has the opposite kind of change that's happening to the ordering cost. As Q goes up, the ordering cost per year goes down. So we are not trying to minimize this cost or that cost by itself, but actually the sum of these two costs. So if you plot the total, if you plot that plus that, and you will see that this is what that curve will look like. We really want to minimize this cost represented by this curve, which means the bottom part, and it so happens, and we can prove this with calculus, that this minimum will occur exactly at the point where these two lines intersect, the straight line and the curved line. So what we can do is we can set these two costs equal to each other and then solve for Q, and that will give us a formula for EOQ. So we set these two costs equal to each other and then do some algebraic derivation, and we end up with this formula. So our EOQ formula is square root of 2 times annual demand times ordering cost divided by cost of holding 1 unit per year. So and then this is the equation summary. So annual hold, once you determine what the Q is, then we can plug that into these two formulas and compute what the total cost is going to be. So annual demand is 1,000, ordering cost is $10, average inventory cost per year is 0.5, then plug them in and you get the EOQ. And then plug them back into the cost. Okay, plug the value of Q into cost formula. Okay, so here number of orders per year, D over Q. So 1,000 over 200 is 5. Average inventory is Q over 2, that is 200 over 2 is 100. And you see that the two individual costs are exactly same. And that's because of that. The minimum cost occurs exactly at the point where these two lines intersect.